Welcome back to Separations. This video is going to be all about the balances and relationships that you can draw between streams in distillation columns. So I've got my detailed process flow diagram back, and I will use this to illustrate some of the key relationships that you can write on a column. The first key relationship is that streams that exit the same stage are going to be in phase equilibrium. Okay, so what does that mean? Let's just pick a stage for sake of argument. We'll say stage 2, for example. For stage 2, it means that the compositions Y2 and X2 are in equilibrium. Y2 and X2 are in equilibrium. So Y2 is there, X2 is there. Like I said, they're both coming off of stage 2, going to other stages. Therefore, we have an equilibrium relationship that we can write between them. So Y2 is equal to alpha times X2 divided by 1 plus alpha minus 1 X2. All right, this is a relationship that we can write between Y2 and X2. So that's the first one. And it applies to all streams. So Y3 and X3 are related in that same manner. Y4 and X4, Y5, X5, all the way down the line. All right, the second key assumption that we're going to make is that the liquid streams in the rectifying section of the column are equal to each other, and the liquid streams in the stripping section are equal to each other. So this is one manifestation of constant molar overflow. Molar overflow. So this assumption says that liquid and vapor flows are constant throughout the two sections of the column. So for example, V1 is equal to V2, and V2 is equal to V3, but V3 is not necessarily equal to V4 because V3, V2, and V1 are all in the rectifying section of the column. V4 is in the stripping section of the column, so it doesn't count. However, V4 is equal to V5, and that is equal to V6. Same thing for the L's. So L0 is coming from the condenser, is equal to L1 is equal to L2, but this is not equal to L3 is equal to L4 is equal to L5. So this may seem like a very strange assumption. Why can we go ahead and assume that? This is an assumption that really makes our life easier, but this is only valid if the following conditions are met. Number one is that the column has to be adiabatic. So there has to be no wasted energy. In other words, every stage has to be well insulated. Adiabatic column is one assumption. Second assumption is that of constant pressure. Third assumption is that the enthalpies of vaporization of the components are approximately equal. So delta H under bar V for component A is equal or approximately equal to delta H V under bar for B. So heat of vaporizations must be roughly equal. And finally, the enthalpic contributions from a temperature change must be small compared to the enthalpy of vaporization. So what do these four assumptions mean practically? I like to think of it as the energy balance is satisfied. In other words, the energy that it takes to vaporize a certain portion of my incoming material to that stream is balanced by whatever is condensing on that stage. So this is all a fancy way, if you combine it, to say that the energy balance is satisfied. I'll say perfectly satisfied in each stage. In each stage by vaporizing or condensing components. All right, so that is going to simplify our lives very much when we consider our third relation that we can write on a column. And that relationship is that all streams coming into or out of the column must be in material balance with each other. So this one is kind of, I think it goes without saying, but very important to recognize. All streams into or out of a particular stage are in material balance with each other. balance with each other. All right, so let's see an example of that. I'll write the example for stage 2 again. So the material balance is of the form in is equal to out. So I have two streams coming into stage 2. It is the vapor, whoops, I mixed this up. This is vapor 3 and Y3, and L has a subscript 1. So the streams that I'm counting as coming into stage 2 are the vapor coming from stage 3, the liquid coming from stage 1 are coming in, and on the outside, I have V2, Y2, and L2, X2. And then since we can say that constant molar overflow applies, we can drop the subscripts as well because V3 is equal to V2 and L1 is equal to L2. So we can simply say Vy3 plus Lx1 is equal to Vy2 plus Lx2. Now, we can't necessarily say again that the compositions from the stages are equal because the compositions coming off of the stage are equal. I'm sorry, the compositions coming off of the stage are in equilibrium. They're not equal. Oops. And the only stage where this is different is going to be the feed stage. So wherever you've got something coming into or out of, I guess we'll also talk about probably some side streams as well. So if I pull something off of a column or if the material balance is perturbed in some other way, you have to account for that as well. So I'm going to draw the stage 3 balance as well. All right, so on the feed stage, I've got stream 4 vapor coming in from the stage below. I've got L2, X2 coming in. And this is what I meant by saying you have to account for the feed. I also have the feed coming in as well on the inside. V3, Y3, and L3, X3 are leaving. And remember that V3 is not necessarily equal to V4 in this case because I'm adding this feed. So these are going to be all the relationships that we're going to need to know in order to solve our first problem, which will be the point of the last video for today. So I'll see you in the last video.